I actually will not have time to talk about quite all of that, and so I will be focusing on evaluating biogenic emissions and looking at the NOMADSS and SEAC4RS data. And we've heard already quite a bit about isoprene, and I think everybody really understands the importance of biogenic emissions, but isoprene is really only half of the global distribution emissions of biogenic VOCs. And so an additional 30% come from 10 compounds, which are highlighted there: methanol, ethanol, acetaldehyde, et cetera. And most of these were all measured during these campaigns, so we can make an effort to try to evaluate them. And then 145 other compounds make up 20% of the rest of it. And the isoprene oxidation schemes we've heard quite a bit about already this morning, but the other biogenic VOCs also play an important role in gas phase chemistry and ozone production. For example, ethanol produces acetaldehyde, which is also directly emitted, which leads to pan formation. So the observations I'm going to look at are from NOMADSS, which was the first half of the summer in 2013, and SEAC4RS in the second half of 2013. And the plots here show the all of the points for the flight tracks were below 2 kilometers, and they were really concentrated over these regions of high isoprene emissions. And so for the additional analyses I'm going to show, I'm focusing on these regions over the southeast U.S. So the standard that everyone is really using to calculate biogenic emissions is Alex Guenther's Megan model, which is based on, for any given point, emissions are calculated based on the leaf area index at that point, the meteorological conditions, the plant functional type with the vegetation type, and then through these Megan algorithms based on a potential emission factor at standard conditions for a given plant type, then a total emissions is calculated. So the Megan algorithms have been incorporated into the community land model, which is a component of the community earth system model, and I'm running CAM-chem, another component of CESM that is coupled to CLM. It's driven by the GEOS 5 meteorology, and for this study so far I'm running it at 2 degrees. So we've recently expanded the chemical mechanism from Mozart 4. A lumped monoterpene is now treated explicitly as 4 different monoterpenes, and a sesquiterpene. MBO, which is another important biogenic emitter in some regions, is included, and we've expanded the isoprene oxidation somewhat to include IEPOX and HPELD. And so we now have, with stratospheric chemistry, about 170 compounds in the mechanism. So to start with, I'll compare the model results for isoprene to the aircraft observations. So on all of the following few plots, the NOMADSS data is on the left, and SEAC4RS data is on the right, plotted as a function of altitude, and I've interpolated the model results to the flight tracks in space and time, and then binned them by altitude to get an average profile. And the model results are in blue diamonds and the data in black points. So for here, we can see that perhaps the isoprene emissions from the model are a bit low compared to the observations, at least right at the surface. But isoprene has a lifetime of only an hour, so this is really quite a challenging comparison to make. There are numerous measurements of monoterpenes, of several of the monoterpenes. So we have alpha-pinene on the top row from NOMADSS and from SEAC4RS, and the model seems to be a bit high in both of these cases. Beta-pinene is in the middle, and agreement is pretty good. During NOMADSS, the TOGA instrument was measured limonene, which is very small levels. It's only a few ppt, but the agreement is good there. And the PTRMS measures total monoterpenes on the lower right there, and so I've summed up all of the terpenes in the model, and that agreement also looks very good. Now, methanol is a very important biogenic emissions species, and it has a longer lifetime, so it's a bit easier to do a model evaluation with it. It has a lifetime of about a week. The emissions of methanol are essentially all from Biogenic, about 90% of the total emissions. And the model measurement comparisons here are quite good as well. So I think Megan is doing a very good job. It might be slightly high, especially compared to the Seeker's data. Acetone has an even longer lifetime. It also has 90% of its total emissions are from biogenic emissions, but it also has a significant secondary chemical production source. So we can't, we have to take some care in really comparing directly the observations to Megan fluxes, but in the model here, the model measurement comparisons here indicate that perhaps the model is too high, and perhaps that means Megan biogenic emissions are too high, but there are also could be sources from outside the region or from other sources. Acetaldehyde has a very short lifetime, but agreement with the observations here looks very good in the in the boundary layer for both sets of campaigns. And then there are a number of other compounds that we don't usually think about as biogenic emitters, but can have a very important source. Ethanol is an important precursor of acetaldehyde, and ethene and propene are indicated in Megan to have a very significant source. The observations suggest that it's a bit lower in these regions, but the lifetime is very short too, so that's needs to be considered. And MBO has been seen in significant amounts in Colorado, but it may not really be emitted in the regions such as Louisiana, where these samples, aircraft measurements were made. But the community land model has only 15 plant functional types. So anywhere that there is a needle leaf evergreen tree will use an emission factor from Megan and cannot distinguish between Colorado and the Southeast U.S., which may be account for these differences. So there are a number of other compounds that were measured during these campaigns, such as the isoprene oxidation products that we've heard quite a bit about the first half of the morning, and we will certainly start looking into those and comparing. For example, there are measurements of MVK and methacrolein and the sum of them, as well as, of course, measurements of formaldehyde, which for these results here, looks like the agreement is quite good between measurements and models. And we have global distributions of IPOX and HPALD and isoprene nitrates that we will work with the observations groups and try to make sense and evaluate our chemical mechanism. So to conclude, I think the NOMADSS and SEAC4RS observations have provided a really valuable data set. We have to remember, though, when we're comparing to Megan, that this is really only just for in the Southeast U.S. and shouldn't make global conclusions about the ability of the model. We're going to be running the model at ½ degree, which should certainly improve the model measurement comparisons, and we'll certainly make use of additional campaigns such as the DC3 campaign in 2012 and all the other measurements made in 2013 at the ground-based SOAS site and CENEX. And we're also going to start looking at the fire emissions, evaluating and improving a variety of aspects of them, including emission factors, looking at agricultural fires and VOC speciation and incorporating that into the model. And that's all.
We have time for a few questions. Yes, Glenn.
So you said that it was difficult to evaluate Megan isoprene because its lifetime is short. But we do have measurements of OH from NOMADSS. So have you compared the models OH, measured OH to see if that lifetime?
No, I haven't done that yet, but that will also help in that comparison.
Yes, Jenny.
You showed that some of the you have a sense yet if that's reflecting the spatial differences, the temporal differences, or both?
No, I don't have a good sense. For a number of those cases, it looks like Megan is actually quite similar between the two cases. So maybe perhaps it's not taking into account the regional differences that, because slightly different areas were sampled or not properly accounting for the seasonal differences. They were also different instruments, so consideration has to be made for the two different instruments. And it's probably well within the measurement uncertainty between the two measurements. Chuck.
You often have some differences in the free troposphere as on these graphs that are pretty significant factors in the two or more. Is that transport related, or is there something chemically going on there that's not being captured from also?
I'm not entirely sure. I think it's probably transport. It's not the local chemistry, because often the models agree very well in the boundary layer, but almost all compounds, not those, but it seems like many of these compounds are the model underestimates in the free troposphere. So it seems like it's probably sources upwind that are not being properly accounted for.
Yes, Ted.
How about petroleum as an emissions source?
I'm sorry, I missed the compound.
Petroleum.
I haven't looked at that. We don't include that in the model, so I'm not sure.
Then I have a question. If you look at the more reactive species, it seems that the gradient down low is much more steep in the measurements than in the model. Have you noticed that too? Or?
Yeah, I
And
think.
why is that?
I think the models have a hard time parameterizing boundary layer mixing, and I think that's something that needs to be carefully evaluated. We need to. So there's probably too strong mixing in the model that's vertically redistributing compounds.
Okay. Thanks. Well, thanks again.